Hello, I'm Jidong. I'm going to briefly talk about our project. So we do distributed database project. And I'm going to first give you a little introduction. Our project goals is doing data sharding for current scalability, data consistency, and then our key implementation are data sharding for member or entities, consistent data product catalog via message queue, failure detection, and custom gossip control encrypted communication, P2P routing, and static file replication. So our motivation is that we want to solve the problem of single node database bottleneck performance, and also distributed system can scale easily, and we also provide redundancy to increase for resilience. So these are the related working system we covered in the final project. So I'm not going to detail in this, but we implement range strategy and hash strategy, and MVCC and P2P true searching. So I'm going to talk about key design choices. So for heterogeneity, we use Spring Boot application, HTTP REST, Cloud MQP, so it can work on any OS. And for openness, we use REST API, RabbitMQ, HTTP request, so any node joining can easily attach to our system. For security, we use SHA-256. For failure handling, we use gossip-based failure detection, and then heartbeat service, and then static file also replicated, and then RabbitMQ also can act as a buffer during failures. For concurrency, we implement MVCC. And for quality of service, we can improve the throughput through sharding. And for scalability, not only can we just add more EC2 instances, but we can also have more data sharding. So each node handle a fraction of the ORAs, which largely share the load. We have consistent hashing, hash table. We can add new server easily and assign a portion of hash space. And transparency, we have location transparency, replication transparency, failure transparency, concurrency transparency. User didn't know that your database or server resides on, didn't know the data or save file are being replicated, and didn't know that we masked no failures, and user didn't unaware of the complicated concurrency control under the hood. Next, I'm going to talk about system architecture. I'm going to use a diagram to talk about this. So all the servers are deployed on EC2, on AWS EC2. Server 1, Server 2, Server 3, Server 4. Server 4 acts as a new join node. And then the MQP, Cloud MQP, we use RabbitMQ. It also built on AWS. So frontend also on AWS. So each have different port number, 8081, 8082, 8083, 8084. And all of them open port 9000 for gossip control. So the request come into the application. If it's product, then goes to the RabbitMQ, and then all the other server can listen and receive the message. And other table just send a response back. Next, I'm going to talk about the component. I'm going to use the component diagram. So the client front end send a request, goes into the controller. Also, we have this controller, and then you goes to the server router. Server router will find the correct node for this request. So if didn't find the correct node, you would just keep finding, going through the finger table and find the next node. And if it found the next node, correct node, then go to the service implement service layer, and then you'll find the correct shard. For example, if the order is 2025, you'll save to 2025 database. So it needs to set the correct shard. And then goes to repository, and then this is divided into two because product didn't have shard. So it maintained by every node, every server. So product goes to RabbitMQ. I'll talk about that later. So for other database, it goes to the SQLite database. Common 1, common 2 is for user, for members. Order have 3, 2024, 2025, and old. And then all these are configured by these classes. And for product, after product was saved to the database, you'll go to the IBMQ or producer, and then push to final exchange, so it broadcasts to all the queries. So all the queries will receive the message and then goes to the service and update the product. So that's our component. Talk about this. I'll leave the gossip protocol to my partner. This is the product update. I'll talk about this. I use product sequence to talk about the product update. So the request come in, the product controller write a signature, and then add or update the product in the product service, and then push to producer and push to exchange, and then final exchange will push to and every server will receive the message because it's final exchange. So the server 1 receive an update, server 2 receive an update. All right, I'm going to give a live demo.
Alright, right now I'm going to have live demo on these topics, on this test case. First I'm going to demo encryption. So I'm going to first explain our test class. This is order security test, and now I'm going to new order. And then I'm going to test safe order with valid signature. As you can see that we use we convert this order to JSON in alphabetic order, and then we use SHA-256 to encrypt with a key. So this key is here, our custom key. And after we get a signature, we'll put it in the header, and then we send it. And next we will test the invalid signature. Invalid signature is just basically give anything to the signature, and also put it in the header and then send it. So we expect the result will be 007 on unauthorized request. So this is the code that we customize. And then next we will test no signature. Basically we just put nothing in the header and then send it. And then we will expect 400 error. And the error message will be required header X signature is not present. And then we will test different endpoints with valid signature. This is the endpoint of delete. So we save it first and then delete. And then this is the endpoint for update, endpoint for find range, endpoint find range local, endpoint get one, endpoint history. All right, let's run through the test. So all the tests successful. So let's see with valid signature. Let's see with no valid signature. With no signature. So we will expect to see yes, require request header X signature for method parameter string is not present. Okay, we finished testing the security, the encryption. We can take a look at how we do the encryption. So in the order controller, each request will have this one, request header X signature. And then again, we convert to JSON in alphabetic order, and then we use SHA-256 with secret key, and then we can get this expected signature, and then we check if this expected signature matches the signature come from the front end. If they're not equal, then we will return this unauthorized request. This unauthorized request is 007 unauthorized request. So basically, this is version signature mismatch. Then we'll, if they match, then you can continue to other logic. Alright, next demo, P2P routing. So for P2P routing, I'm going to use front end to demo and check the log. So we new a member, doggy. We create a member successfully. Let's check doggy. This is all we can see. We just create a doggy member. Let's check server 1, no doggy. Server 2, doggy. So doggy is safe to, it's routed to server 2 and safe. Let's check server 3, no doggy. Server 2, doggy. Let's check the log. Let's see if here we can see to JSON we check the signature, so we can know that current we just created number doggy, and then the expected signature they match, and then final routing number 75. So 75 is bigger than 64 and smaller than 128. So it routes to 128, which is the second server. So you can see forwarding safe member request to this 8082. So let's check. So here we get a doggy. In server 2 we get a doggy, and then we check the signature, and then we go to the routing. So 75 is current node. So it goes to the sharding layer. So searching sharding layer, we will find that this doggy is belong to common 2, shard common 2. So we set the shard key to shard common 2, and then we save it. So that's our demo for routing, for P2P routing. And then next, I'm going to demo sharding. So right now I'm going to demo sharding. So I'm going to demo in the order table. So right now you can see this is the order table from all the servers. And then this is from server 1, server 2, server 3. So I'm going to create an order. Copy, paste 777. Create. Alright, I'm going to look into the log. Wait, I'm going to search it. From all we can see, this is the order that we just created. Okay, this order is routed to the server 3. Let's look at the log. So in the server 1 log, this one, let's see. So in server 1, this 777 order goes to server 1, and then it will route to the hash ID is 162. So 162 is bigger than 128. Yeah, we can see 162 bigger than 110 and smaller than 192. So it goes to the 192, which is the server 3. Let's look at the server 3 log. This one. So it goes to server 3, and then go through the P2P there again, and then it finds out this is the current node, and then it will save the request order. So new order ID, order date, go to the service layer, and then for the shard, so we can see that the order ID routing to shard order 2025. Okay, so this is the sharding, and then you save it. This is the MVCC version 1 saved successfully, and then goes back. So let's look at if we change it. Oh, we cannot change it. Okay, this is the demo of shard. Next, I'm going to demo the MVCC and rollback in the update order. So I only implemented in the update controller. So next, let's see MVCC. Okay, this is the autocontroller MVCC concurrency test. I'm going to walk through the procedure first. First, we're going to create a new order. Okay, so we new an order, and then we save it to the database. And then we'll read it once, duplicate the object. Okay, so we're going to make 2 copies, and then 1 copy modified to 111 price, and another is 999. And then we're going to send both update in a parallel. And then we get it, we return it, and then we will check both results. And then what we expect is that 1 is successfully updated, another is failed. Another failed message will be database conflict, DB conflict. And then in the log, we will expect to see version mismatch. So let's first check the order controller first. In the order controller, so save it, and then the update. So in the update, we will first check signature, signature mismatch will return error message, and then go through the server router, and then next we'll go to service layer to update. So in the update, we'll go through this one, and then we will first we will have a for loop, and trial times is 3. So this is because the first attempt will fail due to the SQLite DB lock, because SQLite cannot remove the DB lock, cannot configure to remove the DB lock. So we will simulate the MVCC by multiple attempts, and here we will try 3 times. So in the second and third time, you will see the version mismatch. So in here, we will first check. We will get the current order table from. We'll get the current order from the order table, and then we will check if the 2 version, the expected version and actual version, if they match. If they didn't match, we will throw this exception version mismatch, and then if they match, we will update we will first expire the current version, and then we will insert a new version, and then save it to the current repository. And then, yes, and this is we use Entity Manager to do this because we want rollback. If anything, any exception happens, we want to roll back. So we create a new Entity Manager, and when we get transaction begin, we merge the current, we persist the new order, and then we commit at the end. So if any exception happens, we roll back. So this is a exception in first time will happen is that the DB is locked, and then we will sleep it. Basically, we delay another thread a little bit, and then we roll back, and then we go to the loop and do again. So this is basically the MVCC procedure. Let's test. Yeah, so you can see this is checked. It means successfully successfully. The expectation means the result means our expectation. So you can see this is the first one. Worker 1, worker 2. At first, they all read 1, so they all want to update at the same time. So first we will see this DB log, database log. So this is a natural SQLite. We cannot remove that. So, but to simulate the MVCC, we try second and third time. So you see attempt 1 failing DB log. So next time we check worker 2, we found we fetched the current version and we found that the version is mismatched. So expected is 1, but actually it's 2, meaning another server already, another thread already update the current order table. So the worker 2 cannot update again because the version is mismatched. So rolling back, this is the rollback, and due to this is the error message. And the third time we try, we also found the same thing. The version mismatch, the rollback. And at last, this is the result from this test. And then we can see that one is successfully saved into the database, and then another is 0402. This is the custom code, error code, and then it's data conflict code. Okay. We finish demo MVCC and rollback. And next, we're going to demo the static file upload and replication. So right now, I'm going to first go to the server 1 and then delete the SnowBG because we are going to demo that. No, we're going to save another picture. Let's say let's go to front end. So first I'm going to upload a picture to the server 1. So we can choose. Right now, in the server 1, there are 3 pictures, left banner, BG, and SnowBG. So let's check server 2. Static file, there are also 3 pictures, right banner, left banner, and the SnowBG. In the server 3, there are only 2, BG and right banner. So what we're going to do is that we're going to upload to the server 1, and then it will replicate to the server 2, and then we will use the log to check that. Also, we will use here to check. Okay, I'm going to upload P2P chart. Upload successfully. Let's go see. Okay, let's refresh. In the server 1, there's the P2P chart 16. Okay, let's see the server 2. Yes, it also has this P2P, so it means that it replicated to server 2. Let's check server 3 to see if it goes to the loop. No, so it means successfully only replicate to the next neighbor. So let's see the log. In here, we can see receive locally uploaded file P2P chart 16 JPG, and then you replicate to the second node. Okay. We finish demo the static file upload rollback. Wait. Oh, I forgot to demo the rollback. Okay, I'm going to demo the rollback. I only demoed MVCC, I forgot to demo rollback. So this is the rollback test. Okay, so again, we're going to save an order first, and then we will prepare to update a fake update, and then we will trigger an exception in a service, and then we will expect to rollback. So, so this is update, but you will trigger here we will trigger a runtime extension simulator failure, and then when failure you will roll back, and then we will verify if the version is still 1. Okay, we will find this order ID and verify. So we will see, and then we will verify if it is still version 1. Okay, let's run this test. Okay, it successfully run. Okay, let's see. We save it, you save it. Okay, this is a fake update. And then we try to update with the version 2, and then we roll back transaction due to simulate failure. And then we only find it. Okay, we find it. So this came back. This came back version 1. Okay. And then we find the history. Version 12. So all the history of this. So we can see that version 1. So in the history of this order, it only has 1 version. Okay. In normal situation when we update, you have multiple versions, like change it to no. Like this one, it has multiple versions. But if we roll back, we can only see 1 version. Order history, code, version 1, and then nothing else. So it means that our rollback works successfully. Okay, let's demo the last one, RabbitMQ product update sync. I'm going to use Postman to demo this. So right now, this is the this hits the server 1 product. Oh, so we can see all the products. So all the server maintain this same product list. You can see this is the same product list. So first I'm going to test the sync. Okay, I'm going to add element juice to server 1. This is hit server 1 and add element juice. And then it successfully add element juice. Let's see. Server 1, it has lemon juice. In server 2, also has lemon juice. In server 3, also has lemon juice. In server 4, also has lemon juice. Okay, so let's check the RabbitMQ. This is the RabbitMQ. You can see in the queue we have server 1, 2, 3, 4. Okay, we just received a message. And then next, I'm going to shut down server 2. And then we update and delete. And then we bring back server 2 to see if it receives the message from the queue and update and delete and remain the same data as other servers. Okay, so I'm going to kill server 2. Kill it. Check again. Okay, right now server 2 is being killed. Let's check here. Server 2 is gone. So server 1 is still alive. Right now I'm going to update laptop. This one. Laptop right now is $1,000. So I'm going to update to $30,000. Okay. Let's check server 1. Okay. Laptop is being updated. Server 3. Laptop update to 30,000. 30,000. So the servers are updated. And then let's delete. We delete the monitor. So this one is the monitor. Delete. Monitor is gone. So you can see monitor is here. I'm going to select again. And, okay, monitor is gone. And here, monitor is here. Select. Monitor is gone. Here. Yes, monitor is here. It was here, and then select, and then monitor is gone. So right now I'm going to bring back the server. Re-enter. Okay, server 2 is back. So let's see. Okay, we can see that the laptop is updated 30,000, and then let's see no monitor. no, not here, it's here. So means that server 2 read the message from the queue and then update and maintain data consistency with other servers. In server 3, we can see the processing consumer. We receive a processing message update laptop to 30,000. Yeah. And then it should have another processing. Let's just use. This is the laptop, and this is the delete. So we delete the monitor. Okay, we delete the monitor. And then let's see other third server. Server 1. In server 1, we can also see that update laptop and delete monitor. Delete this ID one. This update. Delete ID. This one. This is the monitor. In the server 4, you can also see update laptop and then delete monitor. So in here we can also see in the server 2, the one that down and came back, we can see update and then delete. Yeah, so that's our demo for RabbitMQ. Thank you.
Hi, I'm Hopin Gao. Now I'm going to introduce some functionalities of our distributed database system, including gossip algorithm, heartbeats, and the hash reallocating mechanism. As you can see over here, we have 4 hosts. From 1 to 3, they have a fixed hash in the configuration table, and host 4 is a dynamic hash host, which means every time it recovers, it will reallocate its hash to others. Every 30 seconds, the node will send and receive a heartbeat message to every other nodes. And every 60 seconds, they will broadcast every node's finger table to others for synchronization. We can see it, yeah, over here. And let's emulate that what will happen if one node shut down. Let's do it first. The fixed hash node. I will queue it to emulate it has shut down. As we can see over here, it's received a host down message from host 2, cause host 2 detected the failure of host 3 from heartbeats and sent gossip to others. We can see over here the table has refreshed every node. Let's restart host 3. Because host 3 has a fixed hash in its configuration file. So it's just simply adding itself to the table and sends a host add message to everyone. You receive a host add, and instead it's added to the finger table. Size has changed. And let's focus on the dynamic hash allocating. Let's shut down this one. Mm. And just like hole 3, every node refreshed its table because hole 3 has shut down. Yeah, the set has changed because receiver shut down message, got a message from host 2. And let's recover host 4. Firstly, it will ask other fixed hash hosts for their uh sorry, wait a sec. Ask for their complete table, and after it receives the current finger table, it will find the optimal hash for itself and do its two-phase commit. First, send a proposal to all the nodes, then check if it receives more than half of the confirmation from the nodes. After confirm and approve the hash, it will send confirmation to other nodes. Then dynamically allocate the hash and sends the new hash and the IP to all other nodes. You can see the finger table size has renewed. And look at other hosts, we can see they approve the hash proposal, receive proposal, accept proposal, and receive confirmation. And that's the end of my part. Thank you. After the demo of our implementation, then we continue on the simple overall impact and evaluation of our project. Firstly, our heartbeats and Gaussian mechanisms help detect node failures and inform other nodes about updates. And after the failure has been detected, we only need about 10 milliseconds to inform other nodes. By doing this, we avoid sending requests to nodes that have been shut down. Also, we measure the lag for product updates. The worst case delay between one node publishing an update and other nodes applying is about 0.3 seconds. And this propagation ensures that product catalog remains eventually consistent. We use the MVCC to ensure that one request will be rejected if there's a version mismatch. It successfully prevents lost updates and maintains consistency. Obviously, there's a lot of imperfect part of our design and implementation. Firstly, we only have one replication for static files, no replica for other files. In this case, if one database, one host shut down, we need to wait it to be recovered, and yeah, more replica for static files is better. Also, when our system grows and we need a dynamic balancer, like for example, one node with certain has too much work to do, we can dynamically create a neighborhood a neighbor host to share its workload. And what's more, for use case requiring strong consistency, like a transaction, we need to ensure ACID across shards. To sum up, we build a functional distributed systems that has horizontal scalability and failure handler. By sharding data across multiple nodes, we improve throughput and availability over a single node design. The system achieves over 1,200 requests every second throughput. We demonstrate effective solutions to key distributed system challenges, including scalability, fault tolerance, consistency, and concurrency. And that's the end of our presentation. Thank you for listening.